to a new session of Graviticulas. So our speaker today is Benjamin Guiot. No sé, I don't know how to pronounce your last name.
Guiot.
Guiot. So Benjamin started his PhD in 2011 in Sabatec in France, Nantes. So under the supervision of Klaus Werner. So there he studied physics of quark-gluon plasma and also cold nuclear effects in proton-lead collisions. So during this period also, he implemented the physics of heavy flavor and direct photons in the EPOS event generator. What else? So in 2015, Benjamin arrived at Federico Santamaria with a postdoctoral position. He worked with Professor Boris Kopeliovich on hadronization, and in 2018 he got a position of investigator at Santa Maria University. So nowadays Benjamin is working on hadronization, J-psi production, also heavy flavor production with the kt-factorization formalism. So we would like to invite Benjamin to tell us more about D and B-meson production with this kt-factorization formalism. So Benjamin,
okay.
We are yours.
Okay, thank you for this introduction and for the invitation. So I guess I should share my screen. Okay, so is it okay like this?
Yes.
Yes.
Okay, so it was in fact a suggestion of Edson to do a presentation here. So thanks again for the invitation. And so I decided to present a project with a paper published last year in collaboration with Andreas van Ameren, which is working in Poland. And it is about D and B-meson with a formalism which is called kt-factorization. And with a specific scheme, I will give more details on this. So I guess you all know at least a bit about the pattern model, but I will first give a short introduction on what are the factorization theorems. I guess you already know a bit, but just to remind. Then I will speak more specifically about heavy flavor production and how why we decided to work on this. And then I will just show some results on D and B-meson. And finally, if I have time, I will maybe talk about this more technical issue about the 2-to-1 process. Okay, so just to do a very short introduction. So as you know, in QCD, we have some particularities. So for instance, we have an issue with confinement, which is the fact that you cannot produce free color charge. And also you have some non-perturbative physics due to the running of the coupling constant with energy. So basically at low energy, you have non-perturbative physics, and so you cannot use perturbative techniques. So the first issue is that you cannot produce a beam of free quarks, but at the same time, so you can produce a beam of proton, for instance, but the QCD Lagrangian tells you about the interaction of quarks. So here you have an issue. And so the solution to this are factorization theorems. So basically, what we mean by factorization is this kind of equation here. In the case of CDs means semi-inclusive deep inelastic scattering. So it's similar to DIS. So you have a lepton here, which has interaction, can be electromagnetic or strong interaction with a pattern here, which can be, okay, on these simple Feynman diagrams, this is an electromagnetic interaction with a quark. And so if you detect at the end the electron here, and also a hadron here, for instance, a pion. So in that case, it's called semi-inclusive deep inelastic scattering. And in that case, you can see that the physical cross-section here can be factorized into a PDF, so a pattern distribution function, with a convolution with a perturbative calculable cross-section. So this is the Partonic cross-section, which can be computed perturbatively. And finally, you have this fragmentation function here. So these two functions in red are non-perturbative, so you cannot predict them with a perturbative calculation, and you need to extract them from data. So basically, what you do is that you compare your this equation with data, and so you can extract the PDF and the fragmentation functions. And an important properties of this non-perturbative function is that they are universal. It means that once they are extracted, for instance, in DIS of our fragmentation function in E plus, E minus, then you can use them in proton-proton collision. And this is why you can do true predictions. Okay, and so in fact, just in CDs, just in semi-inclusive deep inelastic scattering, you have in fact a lot of different factorization theorems depending on which kinematical region you are studied. So here, this is just a small graph. It's not necessary to explain everything, but for instance, if you are at central rapidity, Y here is the rapidity and large transverse momentum, so you can use the usual collinear factorization, which is basically like the pattern model, but from QCD. But now, if you are at small qt and still in the and if you go, for instance, at forward rapidities, then here you will need another kind of factorization theorems, and etc. So depending of the kinematical region you are studying, you need different kind of factorization theorems. And in my case, I am working. Can you see the title here in the top of the page?
Yes. Yeah, yeah.
Oh, okay. So because it's not my case. Okay, so in my case, here I did a calculation something which is called kt-factorization or high energy factorization. Originally, the goal of this was to resum some large logarithm, because sometimes when you do perturbative calculation, you can have this kind of logarithm of 1 over x. And so if x, you know, it is the typical Birken variable, so it's this x, it's more or less, it gives you the fraction of the, so the quark, for instance, have a given fraction of the proton longitudinal momentum. So x means this. And if you go to small x, we'll get some large logarithm, and you need to resum this logarithm. And this is done with the equation which is called BFK. And okay, so you have this factorization theorem for the differential cross-section, where basically your physical cross-section is given by a convolution with two unintegrated pattern distribution, so an integrated PDF. So here you have two PDF because we are working in proton-proton collision. And here again, it is the Partonic cross-section, which can be computed perturbatively. The difference between collinear factorization and high energy factorization is that okay, this Partonic cross-section is computed a bit differently because it is off-shell and not on-shell. So this is a technical difficulty, I'd say. And so the main difference between high energy factorization and collinear factorization is that in case of collinear factorization, the PDF depends only on x and on mu square, which is a factorization scale, which has the same meaning as a renormalization scale, okay? Because the bare PDF are ultraviolet divergent. So you need to use renormalization, and then at the end of this, you have a dependence on this scale. But it depends only on X. So you have an information on the longitudinal momentum of the quark or of the gluon inside the proton. But in the case of this formalism, you have also an information on the transversal momentum of partons within the proton. So it's you get more information with this factorization theorem. Okay, and so yes, and okay, there is an additional technicality, which is in fact the reason why I did this publication, is because while collinear factorization for Healy flavor production are done correctly, there was an issue with the calculation in case of high energy factorization. And so basically, I did this publication in order to correct some mistake in the calculation. So I need to talk about a bit about what is called a scheme. So when you extract your PDF from data, you can do it differently. So imagine that your data are this cake. Okay, so the data are always the same, so the cake is always the same. But now, when you compute the perturbative cross-section, you can get something like this. And so your factorization theorem, it is a product of PDF and cross-section, okay? So if your cross-section is this part in blue, then you will deduce that your PDF is this part in red. But if your cross-section is this part in blue, then you will deduce that your PDF corresponds to this part in red. And so you can see that there is, depending of which scheme is used, you will not get the same PDF. So later, when you will do a calculation, it's very, very important to use PDF and cross-section, which has been determined in the same scheme. So for instance, you can compute the cross-section using PDF extracted in a fixed flavor number scheme. And in that case, you need to use partonic cross-section also computed in the fixed flavor number scheme. Or you can use PDF extracted in a variable flavor number scheme. And in that case, you need to compute, you need to use a partonic cross-section computed in the variable flavor number scheme. But what you should not do is to mix these two objects. So for instance, if you compute the cross-section with PDF in a variable flavor number scheme and cross-section computed in a fixed flavor number scheme, you will have some issues. And in fact, it is what was done with high energy factorization. So people get some issues in the calculation, and you can argue that basically, if you do something like that, which is done in fact in the literature, so you expect to underestimate the cross-section by about a factor of 4. Okay, and surprisingly, so now it was kind of a mystery, because surprisingly, people use this mixed scheme. So now this, I will call this a mixed scheme, which is not a real scheme, it's a mistake. And people were using this mixed scheme, but at the same time, the cross-section was not underestimated. So it was quite surprising. And to make the explanation short, what happens is that they used too large. So the expected underestimation of the cross-section was compensated by the fact that they used too large PDF. So here you can see that this is a plot for different unintegrated PDF. So this is a plot for different kind of functions like this, as a function of the transverse momentum here. And so you can see that usual PDF, like the one in blue or the one in pink, they fall off very fast. So basically, when you compute the cross-section, you will get a contribution of this PDF on this range. And nearly no contribution on this range when you do the integration on the transverse momentum. But if you use this KMR unintegrated PDF, you can see that the tail of the distribution is much larger. And in fact, you can show that this tail gives a too large contribution. So now the too large contribution of this distribution compensates the fact that this mixed scheme should underestimate the cross-section by a factor of 4. And at the end of the day, what they get is kind of more or less correct result, but not so precise. And so basically, okay.
Sorry, Benjamin.
Yes.
Can you go back to the previous slide, please?
Yes. Here.
Yes. Can you explain again what's the meaning of this each line KMR, BO, PB?
Yes. So it is a plot of this function, which is called, it's like a PDF, but it's called unintegrated PDF because it depends also on the transverse momentum.
Mm-hmm.
And you have different kind of models for these non-perturbative functions. And so this name corresponds to different, all these three lines are for the gluon, okay? This one in green, just forget it, it's for the charm. And so here for a fixed value of x and a fixed value of mu square, it is plotted the distribution of this function as a function of the transverse momentum square.
But they are, you said that all these lines are calculated by some method?
Yes.
And what's that method?
So it depends. It depends on the model. I think I will show maybe one slide on the KMR, but it depends. But basically, they can be built from the collinear PDF, so from the usual PDF, or you can extract also this function directly from data, again by doing a comparison between the data and your cross-section were expressed as a convolution of this non-perturbative function with the perturbative cross-section.
Okay, thank you.
Benjamin,
Okay. Yes.
Benjamin, in the same slide, mu is the scale.
Yes, it's a factorization scale.
Okay, how is it chosen, the value, the numerical value?
You should choose it equal to the hard scale, because so if you note the hard scale q, when you do perturbative calculation, you have logarithm of mu over q, and you want this logarithm to be small. So basically, you choose mu equal to q. And so if you are looking to, for instance, if you are looking, let's say, to a jet, projection of a jet, and if your jet has a large transverse momentum, so the hard scale of this process will be the transverse momentum. And so you need to choose the mu square equal to transverse momentum square.
Okay, thank
In
you.
DIS, the hard scale is the q square, so you choose mu square equal to q square.
Okay.
Of course, it has dimensions of energy, right? Because
yes.
it appears
yes.
the 10. Mm-hmm.
And yes, so if you look at the cross section, you can see that there is an integration on kt from very large value. So you can see that if the tail of the distribution here is much larger than these two distributions, then you will get a much larger contribution to the cross section. And in fact, you can show that if you cut this tail here, you reduce the cross section by a factor of 3 or 4. So at the end of the day, here this function, when you use KMR, it is about 3 or 3 times too large, and at the same time, this mixed scheme should underestimate the cross section by a factor of 4, and so basically they compensate these two mistakes, let's say, on these two strange things, compensate each other, and you get a more or less correct cross-section. And okay, and so our main goal with Andreas was simply to do this simple calculation, simply at leading order, but to do it consistently by building some PDF in one scheme. So we choose the variable flavor number scheme, and to compute the cross-section in exactly the same scheme. And surprisingly, it was not done up to now. So it was our main goal. And to show that if you do this consistently, you will improve the description of the data by theory. Here are some details about how you build this KMR PDF. But I'm not sure this is the most interesting part of the presentation. But basically, you can see that here is the definition of your unintegrated PDF, and you can see that it is built from the collinear PDF, which depends only on two variables. So here the x, which is equivalent to this x, and here the kt is because, in fact, it should be mu, but here the value of mu is chosen to be kt. Okay, and here you have something which is called Sudakov factor and etc. And here this is the typical splitting function, which you know appears when you compute the radiation, for instance, of gluon by a quark. So when you compute the cross section, typically this splitting function will appear. Okay, it's not really. It does not really matter. What matters is that in our case, we built this function using collinear PDF extracted in a variable flavor number scheme. And we will compute the cross-section within the same scheme. So here, this is just a comparison because this unintegrated PDF, once they are integrated up to mu square, they should give back the collinear PDF multiplied by x. So this plot is just to check that. The dotted line corresponds to the right-hand side here, and the full line corresponds to the left-hand side of this equation. And so you can see that globally you have a good agreement between different lines, which shows that these unintegrated PDF are built correctly. And okay, and so finally, as I said, this is so now we want to consider first D-meson production, and basically we have all these kind of diagrams. So these kind of diagrams where you have an initial charm, it is called flavor excitation, and when you produce the charm, for instance, with a collision of two gluons, these kind of processes are called flavor excitation. Usually, people were using only this contribution, which means that they were working with a fixed flavor number scheme, but at the same time, they were using PDF extracted in a variable flavor number scheme, which is why they should underestimate the data. Because in fact, they consider that this process is negligible, which is in fact not the case. This process, the charm gluon to charm gluon, is in fact the main contribution to D-meson production, and it was neglected. You need to choose the mass of the charm for your calculation, but again, it's not a free parameter because when people extract PDF, they do it using a specific mass for the charm. And so then in your calculation, you should use exactly the same. So in our case, we use a PDF extracted by the CTEC collaboration. They use a charm mass of 1.3 GeV, so we use exactly this value. And the final, one of the last ingredients is that you need to transform your charm into a D-meson, and you do that using this function D, which are called fragmentation function. And you can see that again, so you have a convolution between the cross-section for the production of a charm and this function which transforms your charm into a D-meson. Okay, and here again, so you have different kind of fragmentation function, and we used one called Peterson. So we use Peterson's model. which has just one parameter, and so this is the typical value of parameter. We did not try to tune it. And the last ingredient is that now, okay, this D function, this fragmentation function transform your charm into a D-meson, but you have different kind of D-meson. So you need to say, okay, this fraction go to D0 meson, and this fraction go to D plus meson, etc. And again, these are not free parameters. There are these values are known and published. So we just choose the usual value, and we did not try to tune this value neither. And here, so it kind of answered to the question, I don't remember who asked, but here is our choice for the factorization scale. So you can see that typically it is chosen of the order of the transverse momentum of the D-meson. Okay, and so these are our calculation here on the left compared to Alice data. And here I put some older calculation which are done with this mixed scheme. So here again, people, they just consider the production of, they just consider the process gluon to CC bar, but did not include other processes. So it means that they work with a fixed flavor number scheme, but at the same time, they used PDF extracted in a variable flavor number scheme. And so you can see that at small PT, it's okay, but you can see that at large PT, they have some issues. So here there is a mistake by about a factor of 2 or 3, while in our case, you can see that we did a kind of better description of the data. So this is for D0 at 5 TV. Here is the same plot at 7 TV. So again, there is within. I should mention, so the blue line is the calculation for central value. And so you have a lot of uncertainties. In our case, we take into account just the uncertainty related to the choice of this factorization scale. So what you do is that you know that the factorization scale should be chosen of the order of the Hart scale, but it's not clear exactly what value to use. So what everybody do is just to change a bit the value of mu square between a factor of 4, basically. And so it gives this error band in blue. And we also did a calculation for B-meson, so it's exactly the same as for D-meson. The mass of the bottom is chosen to be 4.77. And you can see here that, again, we did a quite good description of B-meson production. So this is at 7 TV, at forward rapidity. And this is just to show. So here, this is our calculation is for the full contribution. And this is just to show a contribution of flavor creation process. So this green line typically come from the gluon contribution. And this red line typically comes from gluon charm to gluon charm contribution. And so you can see that if you sum these two contributions, you get a shape which is not trivial, in particular at small PT. So you can see that if you include only the green line, it will be hard to describe correctly B-meson production. Okay, and so this is again the same calculation for D0 meson measured by the Alice collaboration at 7 TV, but now compared to two other theoretical calculations. So for instance, in this pink dots are calculation made by Maxim Nefedov and Vladimir Saleyev, where they consider two gluons which go to one gluon. So the R here is okay, some technical vocabulary because it's a rigid gluon, but let's say this is just gluon to gluon and gluon to CC bar. And for this process gluon to gluon, so they use a fragmentation function which transforms the gluon into a D-meson. Okay, and so this group, for instance, it uses this mixed scheme, which again, you should not do that. You should not mix these two schemes. And so you can see that, okay, here is the ratio of data with the prediction. So the issue is that they did a prediction on a very limited chemical range. So it's hard to say if it's good or not. And this is prediction by another group. So now it's these red triangles. And you can see that they are quite below the data here by a factor of 2 about. So you can see that basically our calculations are a bit better. I will not say that the difference is huge, but it's better. If you go to forward rapidity, it's even clearer that our calculations are working better. And if you look to B-meson prediction, it's even clearer. So here the calculation by Maxime Nefedov completely explode. And the other group, they even didn't try to do prediction for B-meson. And that's all more or less. So, okay, if you want, I can do a comment on this. But I think it's better to do the conclusion. And if you want, I can do a comment on this last slide. So the reason why we did this paper with Andreas was really to insist on the fact that you should not mix this scheme. And some people use kind of complicated calculation and everything, but finally it's not working so well. In our case, basically, we just do a leading order, a simple leading order calculation, but doing it very carefully, using the same scheme for PDF and cross-section, and also being careful with the choice of the charm mass, etc. And what we see is that we get basically better results. And what was maybe surprising for some people is that this cross-section is larger than this cross-section. Why it is surprising? Because you have much more gluon than charm. So people, they just assume that, okay, here I have 2 gluons, here I have 1 gluon and 1 charm. So because the PDF for the gluons is much larger than the PDF for the charm, this cross-section should be larger. But of course, it's just half of the reasoning. You should also look at the cross-section. And in fact, this cross-section, even if the charm PDF is smaller, it is larger because it's a cross-section in a T channel and it's very large, and this one is smaller. That's all, but people were surprised. And that's all. Thank you.
Okay, thanks a lot, Benjamin. Quite interesting talk. I don't know if anybody has more questions to Benjamin.
I have a question.
Mm-hmm.
You mentioned it we are seeing it in the first line of your conclusions. It is kind of surprising that people are using mixed schemes.
Mm-hmm.
So, and in fact, you cure it. But do you know why they were using mixed schemes? They should use the same one.
I'm not sure. So, as I said, people assume that this contribution was small, and so it's maybe. So maybe they were not thinking that they were using a mixed scheme, because if here, basically here you need to use this variable flavor number scheme, and if you want to use this, you need to include this process. But okay, if this process is small, you can simply neglect it. And so people, they thought that this process was negligible. So this is one point, one reason, I guess.
I see. And my other question is has to do with theoretical uncertainty on the scale. I'm not sure if I follow what you said. It's around slide 17 or something like that. So
Yeah.
you did check the uncertainty due to the scale. I mean, you change the scale to the twice and half and calculate the observable.
Yes. So in fact, this factorization scale, it is a renormalization scale. So it is an unphysical scale. So the physical cross-section should not depend on it. But
yes,
if you do perturbative calculation, it will be the case if you were working to all orders, right? But for instance, if you are working with perturbative calculation, then if you are working, let's say, to alpha s squared, then you have a dependence on the factorization scale at the order alpha s to the 3.
I see.
And so basically, what is said is that your physical cross-section has a residual dependence on this factorization scale. And so yes, basically, you just compute the cross-section once with the central value, another time with this value, and another time with this value. And it gives you the lower and higher values of cross-section.
Okay, thank you.
More questions? Okay, I have a couple, but might be, for me, this subject has always been very hard. I guess if you don't really put your hands on the calculations, at least in my case, I have always been kind of wondering how you do all of this. But can you please go to slide 9? And then maybe slide 22, I guess both questions are kind of similar. So here, using all these different techniques, you see quite different results.
Yes.
And how does this really like affect simulations? Because then afterwards, when we do, well, at least in my case, when I'm doing the analysis and I'm taking simulations and I am comparing with data, it's actually working. So I have always wondered how all this difference then afterwards affect the simulations. So I don't know if you can give me an answer on this.
I mean, if instead of this red line, you use this pink line, you will get a very different result. But in case of collinear factorization, I think that people are using this since a long time. There are more people working on it, and everything is under control. But in high energy factorization, for some reason, there was this tradition to use this PDF and to use just the Guiot contribution. But it's changing. But
the fact that we do find, I don't know, good results, it's because we are always kind of comparing this with data in some controlled regions. Is it like this? I don't know if you understand.
I mean, I don't know exactly with which model you are comparing your data, but usually I will say that people calculation are done with collinear factorization, and so here everything is under control. There are not large discrepancies like in high energy factorization. So
okay.
I think that in the model you are using, they are not based on high energy factorization. And here, as you can see, if you look, you can see that here there is no good agreement between data and zero.
Yes, I see. So then my other question was on slide 22. So why is it like going so bad for the pink one? So is this because also you said they're using the mixed scheme?
Yes, but I think this is not the only reason, because here the discrepancy is really too large. So maybe they have some other issues with their calculation. Here, I guess at larger PT, calculation are always simpler. And here, I will say that, okay, a factor of 1.5 is probably due to the fact that they use mixed scheme. But here, a factor of 3, I don't know. I guess that sometimes theoretical calculations are valid only in some kinematical range, and maybe 5 GeV, which is more or less the mass of bottom. So I guess that here you have some mass effects which are not correctly taken into account, something like that.
Yeah, I see. More questions? Okay, so if not, I would like to thanks again, Benjamin, and thank everyone to connect. And I guess we see each other next week. So thanks.
Okay. Thank you.
Thank you very much.
Thank you.
Thank you very much.
Thank you, Benjamin.
Benjamin.
Bye.
Thank you, Benjamin.
Bye-bye.
Bye. Ciao.